Hello everyone, this is Chengge Yang and Fei Yuchen. Our final project is using policy gradient and double DDQN learning for playing 4 OpenAI gym games. The 5 sections are listed here. First, we use policy gradient to solve the card pull game. In the policy gradient model, we use a neural network to compute the probability of taking ejections, with 3 hidden layers and 10 neurons at each layer. The training history is shown below. Despite oscillation, the reward keeps increasing and converges after 1,000 episodes. The result is very good. The pendulum is kept inverted all the time. Next, we apply policy gradient to a more difficult task, the bipedal worker game. The game has 24 input states and 4 output continuous actions. The 4 actions are the 4 torques of the legs. For each torque, we discretize it into 9 values. Since there are 4 torques, the resultant action space is very large, which is 9 to the 4, more than 6,000. The neural network we designed is also very large, which has 1,000 neurons at one of the layer. The training result is not good. The robot keeps falling down. Since direct training doesn't work, we try to pre-train the model by using the data collected from Good Policy. The Good Policy is from OpenAI Gym's official website. We pre-train our model on this data. The training accuracy is 82%. The pre-training result is shown here. We see that the robot could stand for a second but fell down soon afterwards. The pre-training is not working well. We guess this is due to the fact that the action space grows exponentially with respect to the device per action, which is too large. In future work, we will read more papers to seek for the solutions.
Then I used the DDQN learning with double neural nets to play with the gym mountain car V0 environment. It has 2 input states and 3 output discrete actions, which makes it quite easy to play with. The only thing is that it only has -1 reward for each step taken, and no positive reward for any goals achieved. So in the training, the reward remains quite low for the first 300 episodes, and it rises suddenly after that and converges quite well. So in the demo, you can see that this model works very well on this environment. The next environment is the pendulum V0. The problem with it is that it has one output, which is the continuous action. So in order to use the DDQN learning, I discretize it to 11 action bins, and which means that the neural nets output 11 probability of those action bins, and I will take the maximum one. In the training, the reward rises very fast and converges very well. And this is the demo shown. You can see that there's an angle between the final pendulum position and the vertical position. I think this is because the discretization process I made. I think I can improve this through using more action bins. The final environment is the bipedal walker V2. This is extremely complicated. It has 24 input states and 4 output continuous actions. I know that DDQN learning is not suitable for continuous actions, but I still want to have a try. So I made the network pretty deep, very deep, like 8 layers and very big, and I use it to output the action values directly. So in the training, you can see that it doesn't converge. The reward doesn't rise, it doesn't converge, and the demo is very tricky here. So after that, I use the same pre-training data as used in the previous sections, and you can see the training is working very well, but it still doesn't give the right policy. I think the reason is that no matter the pre-training data or the real training data, they are all too noisy. They are both too noisy for the DDQN learning model to learn a good policy. So in the future, we will try more advanced models to solve this game. Thank you.